Hi everyone, welcome back. In this lecture we're going to look at indeterminate forms and L'Hospitals Rule. So what's an indeterminate form? Well, if you think back to when we were working on limits, every time we wanted to just get an idea of what the value of the limit was, the first thing we did was just pop the value in. You know, the limit as x goes to 0 of something. We just took 0, popped it into the function and tried to see what happened. Sometimes we ended up with things that looked like 0 over 0. And that signified that we need more work to do, maybe algebraic simplification or something to that effect. We could have got form like infinity over infinity, again, more work to do. Maybe we got something that looked like infinity times 0. Again, we had more work to do. So the point here is that we got a form for the limit where we couldn't quite determine what the value was. In other words, the value was indeterminate. We didn't have enough information. We needed to use more information, either algebraic simplification or some known results about limits. So these are known as indeterminate forms. Since something of the form 0 over 0, it could be 0, could be infinity, could be anything in between. It depends on how fast the numerator is going to 0 and how fast the denominator is going to 0. Similarly for infinity over infinity, also this type 0 times infinity. Okay, the first function is going to 0, the second function is going to infinity. Is one going to 0 faster than the other one's going to infinity? Are they going sort of at equal rates, in which case they sort of balance out and the limit becomes some particular non-zero finite number? There's more work to be done in these cases. There are also some other cases of indeterminate forms that we haven't looked at yet, and really that's the point of this lecture, is what if we got something like 0 to the power of 0? Well, that's not 1. It's an indeterminate form. We don't have enough information to figure out what this is. It depends on how fast the base function is going to 0 versus how fast the exponent function is going to 0. Other forms are, what if the base function is going to infinity and the exponent's going to 0? Well, if the base function is going to infinity, maybe the whole thing should go to infinity. But if the exponent's going to 0, maybe the whole thing should go to 1. There's some sort of battle going on here. How fast is this base going to infinity versus how fast is the exponent going to 0? Again, this is an indeterminate form. We don't have enough information just by knowing that the base goes to infinity and the exponent goes to 0. We don't have enough information to determine what the limit is. And finally, something of the form the base goes to 1 and the exponent goes to infinity. Again, there's a battle here. How fast is the base going to 1 versus how fast is the exponent going to infinity? Which is going to win out? What's the value of the limit? Is it 1? Is it infinity? Is it something in between? These are the kinds of things that we're going to be looking at in this lecture. When we have a limit that's of one of these types, what can we do? What's the more work we can do to figure out what the value of the limit is? So let's look at an example, something that we've actually seen before. The limit as x goes to 0 of sine kx over x. So what have we done in the past with this? Well, here we have that the numerator as x goes to 0, that goes to 0. The denominator goes to 0. So it's one of these type 0 over 0 limits, an indeterminate form. How did we figure it out? Well, what we've done in the past is we used a result that we already knew. And here's the result we already know. We know what sine of x over x does. So perhaps we can use that here. So what I'm going to do is I'm going to say, well, okay, I've got a k trapped in my argument of sine. So I'm going to match that on the bottom. All right, well, I've adjusted the bottom function. It's no longer k, or it's no longer x, it's actually k times x. So I'll put a k out front to cancel it. So what I've done is I've just multiplied by 1 in a fancy way. That's k over k. Now I focus on this bit here. Now the argument of the sine function is exactly equal to the denominator, and they're both going to 0. So perhaps to make it a little more apparent as to what we're going to do, I'm going to change my limit to be from x going to 0 to t going to 0, where I've just let k times x be this new variable t. And now at this stage, we see that this goes to 1. That's using our known result. So the limit here is k. Okay, so we've managed to work out the value of this limit by using a previously known result. Limit of x goes to 0 of sine x over x is 1. Okay, well, that was a sort of an algebraic way of looking at this limit. I want to look at it from a geometrical perspective. So let's just look at the plot of sine of kx. In this case, for concreteness, I took k to be 3. And I want to compare that, so that's my numerator. I want to compare that to my denominator, which is just x. So what I'm interested in here is, as x goes to 0, what's the ratio of the height of a point on the blue curve over the height of the point on the green curve? Well, as I get closer and closer to 0, the sine function, well, we can approximate it by its tangent line. So I'm going to use the tangent line instead to work out values of the heights of the point in the numerator. And that means, okay, I'm going to temporarily forget about the sine function, because for x close to 0, the sine function is approximated by its tangent line. Okay, so what does this mean? Well, I'm interested in the ratio of points on the red curve over points on the green curve the closer x gets to 0. Well, that means I'm just interested in the ratio of, you can see the equation for the tangent line over here, it's just 3x, y equals 3x. So we're interested in the ratio of 3x over x as x goes to 0. Well, that ratio, the x's will cancel, and we get that the limiting value is 3. Limit of 3x over x as x goes to 0 is just 3. Notice the only information we used there was really the slope of the tangent line and the slope of the line in the denominator. 3x over x, or the ratio of their slopes, 3 over 1. We get a value of 3. If this was just a generic k rather than 3, then we get the ratio being k. And that's precisely what we had as an answer. So in a sense, the big picture point of view, from using the graphs of sine kx and x, we get that the limit of sine kx over x can be obtained by looking at the limit of the ratio of their tangent lines, kx over x. So here's a curious point to note. If I instead look at the limit of the derivative of the numerator over the derivative of the denominator, so instead of looking at the original limit of sine kx over x, I instead look at the limit of the derivative of sine kx over the derivative of x. Then what do I get as a result? I get k cos kx all over 1, and in the limit as x goes to 0, cos kx goes to 1, so we get an answer of k. And here's the question. Is this a coincidence? You know, in some sense, I was led to look at the ratio of the derivatives because of my consideration of the graph. I wanted to know what happens, the ratio of the point on the sine function over the height of the corresponding point on the line. I noticed that the sine function can be approximated by its tangent line, so that naturally led to a question about ratios of the rates of change on the sine function versus the rate of change on the line. So that leads me naturally to look at the limit of the ratio of the rates of change, and we get the same result. Is that a coincidence? Well, let's look at another example. Let's look at limit of the form x goes to infinity, ax plus 1 over bx plus 1. Okay, this is another one that we've seen how to do before. In this case, this was of type infinity over infinity, because as x goes to infinity, the top goes to infinity and the bottom goes to infinity. You know, it's either positive or negative infinity. It all depends on what the sign of a and b are. What happens here? Well, what we did in the past was we factored out an a, or an x, from each term. The highest power of x in the top and the bottom in this case. And now I can cancel off the x's, so I get that that's the limit as x goes to infinity of a plus 1 over x all over b plus 1 over x. And that gives me an answer of a over b. No surprise, we learned in the past that we can do these limits quickly by just looking at the ratio of the leading coefficients. Again, let's make a note of this. If I look at instead the limit as x goes to infinity of the derivative of the top over the derivative of the bottom, then that's going to be the limit as x goes to infinity of a over b, which is just a over b. So again, we get the same thing. And is this a coincidence? You know, in a sense I'm saying, instead of looking at the limit of the original function, look at the limit of the rate of change of the numerator over the rate of change of the denominator. In other words, the derivative of the numerator over the derivative of the denominator. And it turns out we get the same answer. Is this a coincidence? Well, in some sense, we can at least intuitively think probably not, because what's happening here? The limit as x goes to infinity, the top's going to infinity, the bottom's going to infinity. It really depends on how fast. If the top's going to infinity faster than the bottom is, then we expect the top to win out and the ratio to go to infinity. However, if the bottom's going to infinity faster than the top is, we expect the bottom to win out and the ratio to go to 0. But if the top and the bottom are each going to infinity in sort of rates that are proportional to each other, then we expect them to balance out and the limit to be some non-zero number. So this question about how fast the top and the bottom are going to infinity is really a question about their derivatives. What's the derivative doing? So that's why it's sort of natural to think about taking the limit of the ratio of their derivatives. Okay, so both of these, I've sort of framed them in the sense that maybe these are coincidences, but at least through our discussions we sort of inclined to believe that. They're probably not. It has something to do with how fast these functions are going to 0 or infinity. That is, it's related to their derivatives. This leads naturally into a statement of a theorem known as L'Hopital's rule. So what does L'Hopital's rule say? Well, it says suppose you have two functions f and g, and you want to know what the limit of their ratio is. And what you know about them is that they're differentiable, both f and g are differentiable. The denominator may have a derivative of 0 at a, but non-zero elsewhere around a. If I know that either both the top and the bottom go to 0, or both the top and the bottom are going to infinity, then instead of focusing on this limit, the ratio of f over g, I can look at the limit of the derivative of f over the derivative of g. And the value of this limit is actually equal to the value of the original limit of f over g. And this is pretty cool because it says that I can replace the function that I want to work out the limit at with a new function, f prime over g prime, and work out the limit of that, because the value of that limit is actually going to equal the value of the limit that I want. And perhaps, if I'm lucky, the derivative of f over the derivative of g is a simpler function that I can work out the limit of. And we're going to see a number of examples that just work out to be the case. So let's look at this first example. The limit as x goes to 0 of e to the x minus 1 over sine 2x. And we do our first approach when we're trying to compute a limit, and that is just pop x equals 0 in. That gives us e to the 0 minus 1, or 1 minus 1. So the top goes to 0, bottom goes to 0. So this is of type 0 over 0. Precisely the type that we can apply L'Hopital's rule to. So to signify we're using L'Hopital's rule, we just write an L apostrophe H over the equal sign. And this limit is equal to the value of this limit, the derivative of the top over the derivative of the bottom. So it'll be 2 cos 2x. Key important point to note here. I'm not using a quotient rule. This isn't a quotient rule. This is saying that you want to look at the limit of the ratio of f over g, take the derivative of f. That's your new top function. Take the derivative of g. That's your new bottom function. So we've constructed this new function from the old one, but in such a way that the limit of this new function, f prime over g prime, is actually equal to the limit of the old function, f over g. And now if we stare at this one, we say, well, as x goes to 0, the top goes to 1, the bottom goes to 2, and so that's no longer of type 0 over 0. That's a value, that's a limit that we can actually compute just by popping x equals 0 in, and we get a value of a half. So that's very nice, because it means that we could work out the value of this limit, which was of type 0 over 0, and in the past we thought, oh, we have more work to do. We've got some algebraic simplification, or maybe using some special limits to try to figure this out. Well, now we're armed with this very powerful technique, L'Hopital's rule, which tells us, no, just look at this new function, derivative of f over derivative of g. Work out that limit. And if you get a value for that limit, then that's equal to the original limit. Okay, so let's look at another example. We're looking at the limit as x goes to infinity of e to the x over x squared plus x. So just taking an observation here, as x goes to infinity, e to the x goes to infinity. X squared plus x also goes to infinity. So this is of type infinity over infinity. So a perfect place to apply L'Hopital's rule. But before we do that, let's just get an idea of what the answer should be. As x goes to infinity, the exponential function, that's blowing up. That goes to infinity. The polynomial, that's blowing up. That goes to infinity. Which one goes to infinity faster? Does the exponential function grow faster than a polynomial, or vice versa? Which one grows faster? Well, exponential growth is faster than polynomial growth. For large values of x, e to the x is much, much larger than x squared plus x. So e to the x grows much faster than x squared plus x. So we expect the ratio of this limit, the limiting value of this ratio, to be infinite. Okay, so we expect an answer of infinity. Let's actually verify that that's the case. So I want to use L'Hopital's rule. So I look at the limit as x goes to infinity. Derivative of the top, that's e to the x. Derivative of the bottom, that's 2x. What is this? Well, as x goes to infinity, this again is type infinity over infinity. Top goes to infinity, bottom goes to infinity. So what do I do now? Well, let's apply L'Hopital again. L'Hopital's rule applies to limits of the form infinity over infinity, where we just happen to hit that, so we can do it again. L'Hopital's rule. Limit as x goes to infinity, derivative of the top is e to the x, derivative of the bottom is 2. Top's going to infinity, bottom's going 2, so the ratio is heading to infinity. So our limit is infinite in this case. So we got the answer we expected. Now, okay, so what have we actually shown here? We've actually shown that exponential functions grow faster than polynomials. So we looked at this ratio, e to the x over x squared plus x. What happens as x goes to infinity? The ratio goes to infinity. That means the exponential function is heading to infinity faster than the polynomial. So exponentials grow faster than polynomials. That's what we've actually shown here. We used L'Hopital's rule to show that. Now, I said we had intuition that that was the case before we even started this problem and got intuitively the answer of infinity, but we've now verified through calculation that the answer is infinite. So we've actually proven now that exponentials grow faster than polynomials. Okay, maybe you'll say that exponentials grow faster than quadratic polynomials. Well, what if this was a degree 3 polynomial? Well, then I'd just use L'Hopital 3 times. What if it was a degree 100 polynomial? Then I'd use L'Hopital's rule 100 times. In all cases, the numerator will stay an exponential upon differentiation, but the denominator will keep dropping by a degree until eventually it becomes constant, and in which case I can evaluate the limit to be infinite. So we actually do have, from L'Hopital's rule, that we can show exponential functions grow faster than polynomials. Let's look at the next example. The limit as x goes to infinity of ln of x over root x. So again, the top's going to infinity, the bottom's going to infinity, so this is of type infinity over infinity. You may interpret this, and it's probably a good idea to interpret it as a question about which one's growing faster. Does a logarithm grow faster than a square root function, in which case we expect the top to blow up to infinity faster than the bottom, so the limit is infinite? Or does the square root function grow faster than the logarithm, in which case the ratio goes to 0? Or do they grow at roughly proportional rates, in which case the ratio goes to some non-zero finite number? Well, let's have a look. Let's apply L'Hopital's rule. The limit as x goes to infinity of derivative of the top over the derivative of the bottom. Do a bit of simplification now. X goes to infinity of, that's 2 root x over x, or in other words, the limit as x goes to infinity of 2 over root x. As x goes to infinity, 2 over root x goes to 0. So what won? What won out? Did the logarithm go to infinity faster than the square root function, or did the square root function go to infinity faster than the logarithm? Well, since the ratio went to 0, it means the bottom had to be growing much faster than the numerator. So this shows that square root of x grows faster than logarithms. That's what we can sort of conclude from this calculation. For the previous one, we had exponentials grow faster than polynomials. From this one, we have square root functions grow faster than logarithms. So in some sense, we got a kind of a hierarchy here. Exponentials grow fast. Polynomials grow a little bit slower. And then probably we got the power functions probably under there, like x to the 1/2. And then we got the logarithms, which are sort of the slowest growing function. And we can get these relative growth rates by looking at their ratios of the types of functions and using L'Hopital's rule to help us compute the limits by looking at their rates of change. Okay, let's look at another example. Here we're going to start to branch out and look at different types of indeterminate forms. So here we're looking at a form of 0 times infinity. Now if we look at it, what happens as x goes to infinity? Well, this part, x, that's going to infinity. As x goes to infinity, x minus 1 over x plus 1, so that's a rational function. As x goes to infinity, that goes to 1. And then we're taking the logarithm of something going to 1, so this thing is going to 0. So we have the first piece, the first factor is going to infinity, the second one's going to 0, so we have something going to infinity times something going to 0. Something's blowing up whereas something's going to 0, and I'd like to know which one wins out. Does this one go to 0 faster than this one blows up, or does this one blow up faster than this one goes to 0, or are they sort of going at roughly the same rate, in which case they balance out and have a value of a limit which is some non-zero finite number? These are the questions that I need to be able to answer. How fast does x go to infinity relative to the logarithm of this rational function go to 0? It could be 0, could be infinity, could be anything in between. The problem is I don't know at this point, just that it's of type 0 times infinity. I don't know what the answer is. I have more work to do, and the more work is LHospitals Rule. But you might observe that LHospitals Rule doesn't apply directly in this case. It's not of type 0 over 0 or infinity over infinity. It's of type 0 times infinity. So what we're going to have to do is try to maybe rework it so it is of type 0 over 0 or infinity over infinity. One way to do that is to say, well, let's take that logarithm and leave it up top, and let's push that x downstairs as a 1 over x. Now what's happening? Well, as x goes to infinity, the top goes to ln of 1, goes to 0. The bottom goes to 1 over x, where x is going to infinity, so that goes to 0. So it is of type 0 over 0, and now we can apply LHospitals Rule. So we had a little bit of adjustment to make first, but now we're in the situation where we can apply LHospitals Rule to it. So this is going to be the limit as x goes to infinity of derivative of the top. Okay, so that's 1 over the inside, so it's the reciprocal of the inside function, times the derivative of the inside. That's the derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. So I had to use the quotient rule to differentiate that inside function as I worked on the top. And now I put that all over the derivative of the bottom function. That's the LHospitals Rule part. So that's negative 1 over x squared. Now I have a little bit of simplification to do before we can figure out if we can work out this limit or not. So one of these cancels with that one. I have an x plus 1 minus an x minus 1, so that becomes a 2 on the top. I have an x minus 1 times an x plus 1. And that negative 1 over x squared, so that x squared comes all the way up with a negative, so it looks something like this. I see that that's just now a degree 2 polynomial over another degree 2 polynomial, x squared minus 1. And the ratio of 2 degree 2 polynomials as x goes to infinity is just the ratio of their leading coefficients, or negative 2. And so there's our answer. We get an answer of negative 2. So let's just look at this by throwing it into our favorite graphing utility. So I'm going to put the function in and see what it looks like, and we see that as we head off to infinity, the function looks like it gets closer and closer to negative 2, so it has a limiting value of negative 2. And that's precisely what we found. We found that value of the limit. Okay. So again, if you're faced with an indeterminate form of type 0 times infinity, try to convert it to one where LHospitals Rule applies. Let's look at another example. This is of type infinity minus infinity. So we have as x goes to 0, this goes to infinity. As x goes to 0, this goes to, well, it depends on which side of 0 you're coming from. It's either positive or minus infinity. What's happening here? 1 over infinity minus something going to infinity minus something going to infinity. What does that go to? Well, it all depends. Is this one going to infinity at the same rate this one's going to infinity, so they sort of balance each other off, or is one going to infinity faster than the other, in which case there's this increased spread in their difference, and so the difference goes to infinity. We don't have any information at this point other than just the type is infinity minus infinity. It all depends on how fast each one of them is going to infinity. So we need to try to see if we can get L'Hopital's rule to apply here. So the first thing to do is, instead of looking at it as a difference, try to look at it as a quotient, so we can apply L'Hopital's rule. So I write the difference as a quotient now, and it's of type 0 over 0, so we can apply L'Hopital's rule. So that's the limit as x goes to 0 of derivative of the top is cos x minus 1. Derivative of the bottom, I have to use the product rule, so that's sine x plus x cos x. Now as x goes to 0, the top is going to 1 minus 1. Okay, so that's going to 0. The bottom's going to sine of 0, 0 plus 0. So that's going to 0 as well. So we're of type 0 over 0. So we can use L'Hopital's rule again. And look at the limit as x goes to 0 of derivative of the top is negative sine of x. Derivative of the bottom is cos of x. Product rule on the x cos of x, so that's plus cos of x minus x sine of x. As x goes to 0, the top's going to 0, the bottom's going to 1 plus 1 minus 0, so the bottom goes to 2. So the limiting value is 0 over 2, or 0. So we get a value of 0 for our limit in this case. Let's just have a quick peek at this by throwing it into a graphing utility. And we see that as x goes to 0, our function values get close to 0. So the limiting value is 0. Now, this is a pretty cool function. It's got lots of interesting behavior, but the thing we were focused on is what was the limiting value at 0. And in order to figure that out, we had to apply L'Hopital's rule twice in order to get the value of the limit. Okay, let's look at one more example. Now there's a few more indeterminate forms that we haven't seen yet, and that's 0 to the power of 0, infinity to the power of 0, or 1 to the power of infinity. So that means if the base function is going to 0 and the exponent's going to 0, then what is the limiting value of the function itself? We've got 0 raised to the power of 0. What is it doing? Well, we don't have enough information to figure that out. It all depends on how fast the base is going to 0 relative to the exponent, similarly for these other types. So how do we deal with these? Well, we can use our good old friend the logarithm, because it helps us convert exponentiation to products. And we know how to deal with indeterminate forms, which are in sort of the product form 0 times infinity, because we can convert that into a quotient and use L'Hopital's rule directly on type 0 over 0 or infinity over infinity. So that's our key here, is to use logarithms. So let's have a look at this example. As x goes to 0, the base, which is cosine of x, that goes to 1. So this is of type 1 to the power of, well, as x goes to 0, 1 over x squared goes to infinity. So this is of type 1 to the power of infinity. So what is this? Is it 1? Is it 0? Is it infinity? At this stage, we don't know. We don't have enough information. So what's actually going on here? Well, cosine of x is going to 1, but as x gets close to 0, cosine of x is going to 1 from below. It's going to 1 from values slightly below 1. So we can think of cosine of x as always being a little bit below 1, getting closer and closer to 1 as x goes to 0. And the exponent is going to infinity. So we've got a number going to 1, which is always slightly less than 1, to the power of something that's blowing up. So what's it going to? Well, you may think that 1 to the power of anything is 1. Well, that's true as long as the exponent is a finite number. Because here we have that cosine of x is slightly less than 1. So you have a number that's slightly less than 1 being raised to a higher and higher power. So that number is getting closer and closer to 1, but being raised to a higher and higher power. And so you maybe expect that this should be 0, because a number slightly less than 1 raised to a large power is really small. So maybe a number slightly less than 1 going to 1, raised to the exponent going to infinity, might be 0. So is it 0? Is it 1? We have to find out. And in fact, we'll see that it's actually a number between 0 and 1. So let's have a look. So what do we do first? Well, I'm going to let L be the value of this limit. I don't know what it is, but I'm going to call it L. And the reason I'm doing that is because I'm going to want to work with L in an equation in a second. Namely right here. I'm going to now look at the logarithm of L. So in other words, I'm not going to be content with just finding the value of the limit. I'm actually going to go and work what the value of logarithm of the limit is. So that's my first step, is to take the logarithm of both sides of this. The reason I'm doing that is because I want to get rid of that exponent and I want to rewrite it as a product. Now, can I switch the logarithm and the limit? Well, that really depends on whether the logarithm is continuous at the value of this limit. Now, we don't know the value of the limit, but the logarithm is continuous on its domain, so if this limit is in its domain, then we can certainly switch them. So we're going to switch them, and we'll see in the end that the value of the limit is actually within the domain, so this step will be justified at that point. Right now, I'm going to take the logarithm, push it through, logarithm of cos x to the power of 1 over x squared. The exponent will come down, and it'll leave me with the logarithm of the cosine with a 1 over x squared out front. So that means we've got an x squared on the denominator. Now, what is this? Well, as x goes to 0, cosine of x goes to 1, ln of 1 is 0, so this is of type 0 over 0. We can now apply L'Hopital's rule. So that was the goal here, was to try to figure out how I could manipulate this expression, or this limit, to get something that I could apply L'Hopital's rule to. Now I'm at a stage where it's of type 0 over 0, I can apply L'Hopital's rule to it. That's the limit as x goes to 0. Derivative of the top is 1 over cosine times the derivative of the cosine, which is negative sine, so it's negative sine x over cos x. The derivative of the bottom is 2x, so I can now just rewrite this, simplify it a little bit. So that's negative sine x over 2x cos x. Now what do I do? Well, as x goes to, it shouldn't be infinity, I'm not sure why I wrote that there, but it's as x goes to 0. This top should be, well, that's going to 0. So that's 0. The bottom's going to 0 as well. So it's of type 0 over 0, so we can use L'Hopital again. The limit as x goes to 0, okay, the derivative of the top, that's negative cos of x. The derivative of the bottom, that's a product rule, so that's 2 cos of x minus 2 sine of x. And now when we work out the value, the limit as x goes to 0, the top goes to 1, the bottom goes to 2. Actually, the top goes to negative 1, the bottom goes to 2. So we get a limit of negative a half. Now what does this mean? Notice that it's ln of L that we've just worked out the limit, the value of, sorry, not the limit, the value of ln of L. And so that means that L is equal to e to the negative 1/2. And so there's the value of our limit. We have that the value of this limit here, limit is cos x to the power of 1 over x squared, is e to the negative 1 over 2. That's kind of cool, actually, if you think about it, because the function we started with was nothing more than a cosine function and the reciprocal of a quadratic. And yet somehow the natural number e popped up in there. Kind of a cool relationship between cosine and the exponential. And in fact, you'll see in your later math courses that there's an actual deeper connection between cosines and exponentials. Trigonometric functions in general, sines and cosines, and the exponentials functions of base e. At this stage, it might be worthwhile pointing out that although we used L'Hopital's rule twice here to get our result, this second one wasn't actually necessary to apply L'Hopital's rule. We could look at it in another way. So here's an alternate way to look at that second limit. The limit as x goes to 0 of negative sine x over 2x cos x. I can split this up. Okay, I'll bring a factor of a half, negative a half, and then I'm going to group the sine x on the top with the x on the bottom, and then I'll just leave the 1 over cosine x by itself. Now the reason I've done this is because we know the value of this limit. Sine x over x as x goes to 0, that has a value of 1. And that's really the issue here. That's the x here is making the denominator 0, and it's the sine x that's making the numerator 0. So grouping them together like this and getting the value of 1, so using a previously known limit, we get immediately that the value of this limit is 1. Okay, the 1 over cosine x, that also goes to 1 as x goes to 0, so we're just left with the answer -1/2. And there we go. So the key here is to note that as we're progressing through calculations involving these limits, we're using LHospitals Rule when we get 0 over 0. Some cases we may just find that it's quicker to observe that, hey, it's a previously known limit in there, and then quickly jump and do this alternate method. So things to be aware of when you're actually doing calculations. Okay, it might be kind of fun now just to look at the graph of this function. So let's get it into our graphing utility, and here's the graph. Okay, there's a few interesting things to note. There's sort of these gaps in the graph. There's sort of this hook, and then it stops. It might be hard to see why we don't get a continuous graph, and there's actually intervals where the function doesn't seem to be defined. Well, there's a cosine function as the base, so it might be better to look at the x-axis rather than in terms of units of 1, maybe look at intervals involving pi or pi by 2. So we can switch how things are labeled on the x-axis by right-clicking on it, going to graphics, x-axis, and what's the unit we want to use? We'd like to use pi, and maybe we'll turn on a distance of every pi by 2. It'll put a tick on the axes. And so now when we look back at the axes, we see that the intervals where the gaps happen are between pi by 2 and 3 pi by 2, 5 pi by 2 and 7 pi by 2. Oh, these are precisely the places where cosine is negative. Why would there be gaps there? Well, if you have a negative base and you're trying to take a rational power of it, a root of it, well, these things won't make sense. You can't take, for example, the square root of a negative number or the fourth root. So these even roots of negative numbers won't exist. So somehow that's being picked up in the graph here. It's not defined here because for these values of x, the base is a negative number. Okay, so we're interested in what happens as the limit as x goes to 0. We see that the value is slightly bigger than 0.6. I want to see if that's e to the -1/2. So I'm going to just get it to sketch the horizontal line, y equals e to the -1/2. And there we go. We see that the value at 0, the limiting value at 0, seems to be e to the -1/2, which is what we found through our calculations. So that's a nice picture illustrating what we've actually done computationally. All right, well, that's it for this section. Thanks very much for watching, and we'll see you again next time.